Now let's consider the relationship between E0 and the equilibrium constant. One of the beauties of electrochemistry is that we can calculate, yeah, not measure, we can calculate the equilibrium constant from standard reduction potential. Okay, let's see how it can be done. A galvanic cell produces electricity when the cell reaction is not at equilibrium. Okay, potentiometer allows negligible current, so the concentrations in each half cell remain unchanged. If connected with wire, much more current instantly flows until the cell reaches at equilibrium. Okay, do you know what does it mean? Let's see. Let's assume you have a battery. Okay, you have a brand new battery, and then you expect, oh, this battery now generates electricity when I insert this battery into my cell phone. Okay, that's correct, right? But when you use your cell phone, for a long time, and then the battery now will be exhausted, and then what will happen? The battery, the potential, yeah, battery, the voltage will be zero. Okay, you understand, right? What does that mean? Battery now uh, produces, for example, 3 volts, but after a long time, right, battery voltage becomes zero. Chemically, we say, oh, the reaction mm, reached equilibrium. Okay, yeah. So in other words, at equilibrium, the cell potential becomes 0 volt. Okay, you understand? Yeah. And then at this condition, we can calculate the equilibrium constant. Okay? Let's see how we can do it. Let's consider two half reactions. The right electrode, this reaction takes place, all right, and the left electrode, this is anode, and right electrode is cathode, and anode, this reaction takes place. Yeah? For the convenience, yeah, we all the time we consider the reaction in a reduction form. Okay, but later on we will subtract this one e minus 0 from e plus 0. Okay, so don't worry. The important is that mm, we write all the reactions in the reduction form and then apply the Nernst equations. Okay, and then let's apply the Nernst equation, and then cell potential is given by E sub plus minus E sub minus, and this part is the right reaction. There is equation for the right reaction. Okay, here, and then minus and parenthesis, and then there is equations. There's equation for this left electrode. Okay, this one, and then rearranging, yeah, this equation, we get E equals E zero plus 0 minus e minus 0. Right? This is what? This is difference in simply standard reduction potentials. And then we say this is E naught, or E0. Okay, and it's the minus this part. Okay, 0.05916 divided by n multiplied by log of this one activity ratio, yeah, this part. And then let's call this Q, okay, reaction quotient, all right, reaction quotient. When the cell is at equilibrium, uh, Q becomes K, yeah, Q becomes equilibrium constant, and then cell potential, this one becomes zero, all right, yeah, and then rearranging this one, E zero here. Let's no, let's make this whole reaction is zero, okay, and then E zero E naught here equals this part, and uh, multiply by log what, not q but k, because we already considered e equals 0. Okay, and then this is very important. This equation relates standard reduction potential difference with equilibrium constant. Okay, and then another rearrangement of this equation, we calculate the equilibrium constant K equals 10 to NF, 10 to the NF E0 divided by this one, very small number, 0.05916. Okay, yeah, either one you have to memorize it, yeah? Either equations. Okay, so this electrode potential is very nicely, very simply related to equilibrium constant. Okay, this is a very useful relationship to calculate electrode potential difference or to calculate this equilibrium constant. Okay, let's take an example. Yeah. When a complex is involved, let's consider this complete electrochemical cell. All right. So when you see this line notation, and then you have to come up with a image of performing of this cell. Okay, the question is find the cell voltage here. First, let's see. This is another one. This is another example. Let me see. Okay. Anyway, let's consider that this complex, what the reaction here. Yeah, on the right hand side, silver chloride accepts one electron to become silver metal and chloride ion, and E0 naught is 0.222. And here, this is the Nernst equation. And then on the left hand side, this cadmium chloride becomes completely dissociates to cadmium ion and to chloride ion. Okay, and then we write the Nernst equation, which is given by this one, and then we take the difference. E cell potential equals this value minus this value. Okay, and which is 0.764 volt. Yeah, so this is the spontaneous reaction. Here is another way, which is to use KSP for AGCL. Okay, instead of write this way, we can write this silver ion plus electron to produce silver. Okay, then the standard reduction potential is 0.799 volt. Okay, and then we write this equation, and using KSP. Okay, and we can rewrite this the next equation, and then we can get this one, the cathode potential, and it gives just 0.3099 volt. Okay, and this is almost identical here. Okay, and then we get the same cell potential, here 0.765 volt. 1 millivolts, the difference is can be neglected because that discrepancy, that small discrepancy, arises from the uncertainty in KSP. Okay, anyway, we have the same result, but now let's consider. Okay, uh, let's find the equilibrium constant for this simple electrochemical reaction here. Okay, by using E0 values. Okay, this one, the first thing you have to do is that which one is cathodic reaction and which one is anodic reaction. Okay, on the cathode, reduction takes place. So which one is a reduction? This ferric ion accept one electron to become ferrous. So this is the cathodic reaction, and then the E0 is 0.771 volt, and this one anodic reaction is what? This one copper oxidation, but right uh, in the reduction form. So copper ion accept two electrons to become copper metal, and then E0 value is 0.339 volt, and then the cell the difference in standard reduction potentials is this one. We subtract 0.771 minus this value, which is 0.432 volt. Okay, and then the equilibrium constant using this equation, which is K equals 10 2, and the 2 is the number of electrons here. Yeah, to make this reaction, okay, we put here we multiply the 2 constant 2 on both sides, and 2, and this value is the electrode potential standard potential difference, okay, and divide by this one 0.05916, and then the value is 4 times 10 to 14. You see, very large, okay. This is a very large number. Yeah, so it is not easy to obtain, experimentally obtain this equilibrium constant for this reaction, okay, since this one is very large. Direct experiment is what you individually measure this one ferric ion concentration and ferrous ion concentration, and also this cupric ion concentration individually, and then apply the equilibrium constant equation. Yeah, but that is very difficult, okay, since the equilibrium constant is very large. In other words, the ferric ion concentration will be very small. How do you measure this very small concentration of this ion? Yeah, you may have large errors, okay, but using this electrochemical principle, it is very easy. Without any experiment, we can calculate the equilibrium constant, yeah, for this reaction. That's the beauty of electrochemistry, okay. And then let's consider the little more complex reaction, okay, finding K for this reaction here. All right, and let's see this one. This is what ferrous carbonate, okay, FeCO3. It accept that this is white crystal. It accept 2 electrons to become ion and carbonate ion, and then someone already calculated or measured the standard reduction potential for this one, which is minus 0.756 volt. And in the meantime, this one uh, ferrous ion and accept 2 electrons to become ion, and then this one E0 equals 0.44 volts. But now question is to calculate KSP for this ferrous carbonate, okay, ferrous carbonate. Yeah, you see this one, ferrous carbonate, uh, dissociates very little, okay, dissociates into this ferrous ion and carbonate ion. You see, this reaction is not an electrochemical reaction, yeah, because there is no electrons are involved in this reaction. This is a pure chemical reaction, yeah. But using electrochemical principles, we can calculate KSP for ferrous carbonate, okay, yeah. Since we already wrote these two equations, and then if you subtract this second reaction from the first one, and then we get this one, okay, and then since we subtracted the potential difference is, what's the potential difference, which is let me see, I'm sorry, yeah, this must be a minus, okay, not a plus 0.44. I think this is a minus, okay, and the difference in standard potentials is, we take this difference here, then we get minus 0.316 volt, okay, and apply this equilibrium constant equation. In this case, equilibrium constant is KSP, okay, equals 10 to 2, okay, there are 2 electrons here, and then this potential difference and divide by this constant, okay, and then it gives 10 to minus 11. All right, yeah. So without doing any experiments, we can very easily calculate the KSP for this material. All right, and advantage of potentiometric measurement is that it allows us to find the K value too small or too large. In this case, this is too small. It is very difficult to, you know, the chemically, uh, obtain the case P, right? But the previous, example is that K is too large. Also, it is very difficult to, chemically obtain this equilibrium constant. Okay, but electrochemically, it is easy. If you know the electrochemical principles, it is rather easy to calculate this equilibrium constant. Okay, and here is the general form to find K equilibrium constant for the net reaction. Okay, half reaction for the cathode is E sub plus 0, and half reaction for the anode is E minus 0. Okay, net reaction is E 0 equals, the difference between these two standard reduction potentials, and then equilibrium constant K is given by this equation. Okay, which is very simple and very beautiful. Okay, let's take another example. The relating E0 and K. Let's consider this complex, this nickel and glycine complex. Yeah? Around the nickel ion, there are two glycine, the molecules. Okay, so we can write it this way: nickel ion plus 2 glycine becomes a nickel glycine complex, and for this one we can write the equilibrium constant K equals what? 1.2 times 10 to 11, very large. Okay, and we know that nickel ion accept two electrons to become nickel metal, and then for this half reaction, it is already known that standard reduction potential is minus 0.236 volt. Okay, now using these two reactions, we can deduce the E0 value for this equation, this reaction. This nickel glycine complex undergoes electrochemical reaction. This complex accepts two electrons to become nickel, metal, plus two glycine ion here, right? So question is to find E0, okay, using these two reactions. Yeah? And here we write, nickel, this one first here, and then nickel glycine, and this one here, and the E0 value. This one is already known, which is minus 0.236 volts, and this is not known. Okay, but this one, when we take a difference between these two, and then it becomes chemical reaction. The first one, nickel 2 plus and the 2 glycine ion, becomes a nickel glycine complex, and then this one K is 1.2 times 10 to 11. Okay, yeah. What is E0 value? Here, E0 value is the difference, simple difference between these two potentials. Okay, so E0 value, let me see. I'm sorry. This E0 value is given by this one. Okay, it is related to equilibrium constant K. E0 value equals 0.05916 divided by n multiplied by log K. Okay, and is already, K is already known, and this one n is already known, which is 2, and we get this E0 value is 0.328 volt. And then what? E0 value here is the difference between this one and this one. Okay, so we want to calculate this one, E minus 0, this value. Okay, this is what? This value minus this one. Okay, using this one, let me see. Yeah, right. E0 equals plus 0 minus E minus 0. So E minus 0 equals E plus 0 minus E. Okay, this one. Mm. Then we get minus 0.564 volt. Okay, this is this example how uh, it can be done to calculate this unknown E0 value for this reaction. Okay, very simple actually. Let's stop here.